Okay, welcome back. Happy Wednesday. Today we are covering inverse functions and log functions. You will notice that we are back in chapter 1 again, so this is another pre-calc review day. And today's review day is supposed to lead us into finding derivatives of log functions and inverse functions next class, okay? So reviewing those two and then taking derivatives next time. Coming up on Friday, steel drum is due. Coming up on Monday, the pipeline is due. Coming up a week from Friday is our second test. Questions on the calendar. A week from Friday is the test.
Not this Friday.
Okay, so let's take a look on page 37. Here we go. Daily summary. Today we review inverse functions. More specifically, we'll look at log functions as inverses of exponential functions. And this review will help us discover derivative formulas for inverse functions, including log functions, next class. All right, number one is an old AP question. AP is a test that some high school students take when they take calculus or other advanced placement subjects. So here's an old AP question. It's a multiple choice question. If f of x equals x over x plus 1, then the inverse function, f inverse, is given by f inverse of x equals, and then we got to pick the right option here, okay? This is a multiple choice. We're not doing 5 questions. So the question is, do we remember how to find a formula for the inverse of a function? It's a process. First, we're going to change the f of x into a single symbol y, copying everything else. And then we know that a function and its inverse take the x and the y and they swap them, yes? The input becomes the output and the output becomes the input. So that's our next step, is to interchange all of the x's and y's. Again, this is supposed to be a review, so does that step look familiar? Kind of start to remember what we're doing here? And then we're going to solve this new equation for what letter? We're going to solve that for y. This is the hard part of the process, is solving for y, especially because there are y's in 2 different places. Okay, well, I'm not sure how to deal with that just yet, but I don't like fractions in my equation. So how about we multiply both sides by y plus 1? And I'm still not exactly sure how we're going to handle the fact that there are 2 y's, but one of my y's is buried inside parentheses. So we have to unbury it by distributing. So xy plus x equals y. We do. I don't care how many x's we have, though. We just have to get all the y's to merge together and become a single y. And the way we're going to do that is we're going to move all the terms with y to one side and all the terms without to the other. So we're going to take that xy on the left and subtract it over to the right. Yes? Subtract xy from both sides. And then all of the algebra we've done has led to this moment where we can take those 2 y's and compress them into a single y by doing what on the right-hand side? What is it? We're going to factor out that y. Yeah? We're going to factor y on the right-hand side. So copy the left. Y comes out. And what's in the parentheses? What is it? 1 minus x. We see it? All of the other equations had 2 y's. How many does that one have? 1, which means we're 1 step away now from solving this equation for y. So divide both sides by 1 minus x. And then all we'll do here at the end is say, hey, it wasn't really y. What did we really find a formula for? Not just f of x, but f inverse of x. That's what we found. That's the formula. C, always choose C. Okay, so again, the key for the algebra on this one was to unbury all of the y's and then put the y terms on one side and the not y terms on the other side so that we could factor out that y. Questions on that? Okay, so that was a quick review of something about inverse functions. So moving on here to number 2, let's see if we can remember what all of these statements about logs mean. Y equals log base b of x means b raised to what power? Is b to the y equals x. That's what that means. For me, this is just like a schematic thing with arrows. B raised to the y equals x, just always in that order. That is exactly what log means, nothing more and nothing less. It just means there's a corresponding equation that looks like that, a corresponding exponential equation. Every log equation has some corresponding exponential equation. It's just a definition. Okay, same idea here. If there's no base given, then what is the base? It's a 10. So invisible 10 there means what to the what equals what? 10 to the y equals x. So invisible means the base is 10. And then on the last one, okay, the base is invisible, but there's something fundamentally different here. We're not writing log, we're writing ln. Josh? Yeah, so I'll put that up here. ln means base is e. Remember, e is just some magical number. It's about 2.7. So that means this equation becomes e to the y equals x. Good? Okay, so let's take a look at number 3, which is talking about log of 800. It says guess the value of the expression, then we'll use our calculator to find a decimal approximation, and then we're going to write some exponential equation. So we'll do a lot of things here. So first of all, log of 800. Let's just give it a name. How about we call it y? Just to name it. And as soon as we've named it, we can write the exponential version of that equation. What to the what equals what? 10 to the y equals 800. Everyone agree? These two equations are equivalent to each other. They mean exactly the same thing. Okay, if y is equal to 1, we get 10 to the first. That's too small. If y is equal to 2, 10 to the second is 100. Still too small. If y is equal to 3, 10 to the third is 1,000. Too big. So y is between what two consecutive integers? 2 and 3, for sure, right? Which one do you think it's closer to, 2 or 3? Yeah, I mean, 800 is pretty close to 1,000, so probably something close to 3. So we'll say that this is something like 2.8, 2.6, something between 2 and 3, probably on the closer end to 3. You've got, yeah, and so then on the calculator, you guys all know how to just type in log of 800. And the whole point of this exercise is to just make sure you understand when you're typing log of 800, it's something you could approximate, right? Like it shouldn't just be a magical number that pops out of no place. It has a meaning. You can guess approximately what it is, and the calculator can give us obviously a much more accurate guess. And so from the calculator, log of 800 is approximately 2.9, which means that there's an exponential equation we can write. So something to the something equals something. 10 to the 2.9 is about 800. And if I type in 10 to the 2.9, am I going to get 800? Not quite. What happened? I rounded, right? 10 to the, what if we type in more? 2.90309. How about that? That's pretty darn close, right? More digits you use, the more accurate it is. Okay, moving on to number 4, asks us for the relationship between the two functions e to the x and ln of x. What are they called with respect to each other? They're inverses. Right? These two functions are inverses of each other. They're exactly opposite of each other. They undo each other. So that's our answer here. These are inverses. Number 5, what's the relationship between the graphs of two functions that are inverses of each other? Yeah.
Wouldn't it be x equals ln of y?
Yeah, so let's actually piece this out here. So if we go through the process to try to find what the inverse function is for e to the x.
Oh, so we can just call g of x y or y.
Yeah, exactly. Yeah, okay. Okay. All right, what's the relationship between graphs? Two functions. Yeah, Mahendra. So there's definitely a symmetry going on their graphs. Symmetric over. And what you want to do is you want to flip one graph over something and it will land on the inverse graph. But it isn't over the origin. It's over the line y equals x, that diagonal 45-degree line. Symmetric over the line y equals x. So that's true for any two functions that are inverses of each other. And we'll look at a specific example here on the next page. It says sketch e to the x and also sketch ln of x on the axes below. All right, so e to the x, I think we know the graph of that thing pretty well. That is an exponential growth function. Let's just plot 2 points on this thing. If you plug in 0 for x, what do you get? 1. If you plug in 1 for x, what do you get? Is just e to the first, which is about 2.7. So I'm just going to plot 1 and then roughly 2.7. And as I go to the left, I get close to what? The 0 to the x-axis. So we'll just draw something here. Exponential growth. And then when I graph the inverse function, well, I should get points that sort of partner up with 2 that I've plotted already. This was the point 0, 1, and this was the point 1, comma, e. And this is the graph of e to the x. And so if we play the game going the other direction and I say, okay, how much is g of 1 and how much is g of e? So definition, this says ln of 1 and ln of e. How much is ln of 1? It is 0. And how much is ln of e? It is 1. And so that means I've got points here on the graph of g. What 2 points? 1, 0, and e1. And so we can plot those points. 1, 0 is here, and e comma 1, that's about 2.7 comma 1, so maybe here. And if we take all the points on the blue and we just swap their coordinates, which is what we saw happen here, we end up on the graph of this orange thing, and getting close to the x-axis over there looks like getting close to the y-axis over here, and we get something like that. And do we see the symmetry? Flipped right over that 45-degree line, y equals x. Okay, so for what it's worth, I think we're really familiar with the graph of e to the x, but some students struggle with the graph of ln of x. It's just not quite in the toolbox the way that e to the x is. But if you understand this idea of inverses, then every time you draw ln of x, you should be maybe thinking about e to the x. Oh, I just got to flip it over the line y equals x. And you do that a few times, and it sort of ties in this relationship about inverses. Okay, number 7. You should be familiar with the basic properties of logs. Property C is particularly useful. So here are some properties written out. If you have the log of a product, A times B, turns out you can separate that into the sum of two logs, log of A plus B. So products become sums inside of logs. Similarly, quotients become differences. Log of A over B equals log of A minus log of B. Over here, what can you do when you have log of something to a power? That power can come down in the front and becomes multiplication. So log of A to the P is P log A. What is it? Like the chain rule? Oh, with the power rule, power coming down in front. Yeah. Okay. I've written parts A, B, and C, assuming the base is what? 10, because I didn't write it, but it's true for any base. I just didn't put all the little b's in here. Pretty much the only logs that we're going to use are log base 10, which is this, and then ln down here, simply because those are the ones on the calculator. I mean, we got two buttons that say log on the calculator, so we're going to be using those. But you could use log base 17 any place we're doing this stuff. Okay, and then we said that ln and e were inverses of each other, and parts d and e essentially spell that out. If you take ln of e to the x, you get x. The ln and e cancel, and ln and e cancel in the other order too. E raised to the power of ln of x is just x. Note that there is no basic property for log of a plus b. Those top three properties, none of them have a plus b inside. If you have log of a plus b, you can't do anything with it. Product becomes a sum, but there's no formula for sum becoming anything. Okay, so last one here in the demo, we're in a position to be able to solve a new class of equations. Whenever the unknown is in the exponent, use logarithms. Let's try on number 9. So we're going to solve this equation for t. 200 equals 100 times 1.01 to the 12t. This equation wasn't given any context, but it hopefully kind of looks like equations maybe you've solved before. That to me looks a lot like like a compound interest type equation. The 200 is like the future amount of money we're hoping to have. The 100 is what? The current, like the starting amount of money. 1.01 means what? Yeah, there's like an interest rate in there. What interest rate? 1%. The 0.01 is the 1% interest, right? 1 plus R. That's what I see in there. And the 12t, what does that 12 mean? What is it? Yeah, it's the K. And what does it mean in terms of the money? Yeah, this means that you're getting interest every month. 12 times a year, you're getting interest. So that 1% interest we saw wasn't just 1% for the year. It was actually 1% each month. That's what's going on here. Okay, so let's see if we can solve. I see that the variable is in the exponent. There we go. The unknown is in the exponent. And so logs is the right tool, but now is not the moment to use it. What do we need to do first? Divide by 100, right? Let's get that exponential piece by itself. So divide both sides by 100. We get 2 equals 1.01 to the 12t. And now that we've isolated that exponential thing, what are we going to do to both sides? Do what? Yeah, take a log of both sides. You could use log base 10. You could use log base e, the natural log. You could use log base 17. Again, we're just going to pick one of the first two because we have buttons on the calculator. So let's use ln both sides. So ln of 2 equals ln of 1.01 to the 12t. Copy the left-hand side. And then we're going to use that property C from right up above, which says what can we do with the power? Bring it down in the front. So the first thing we write here is 12t. And then I'll put a little dot for times ln of 1.01. All right, that right there is a large part of why we care about logs. It's that step. Where was the variable before? It was in the exponent. Where is it now? It's down in the front. And now that it's in the front, it's available. It's accessible to us, right? So that's why that property is so useful. Okay, so ln of 2 is a number, 12 is a number, ln of 1.01 is a number. So we just got lots of numbers multiplied all together here. So what do I do in one step to solve for t? Yeah. And what else? And also the 12. Let's put them both in there in one fell swoop. 12, put it times here. 12 times ln of 1.01. That's all the stuff that needs to move away from the t. And so on the right-hand side, 12 cancels, ln cancels, and we just get t equals. Okay, so copying the left, ln of 2 over 12 ln of 1.01 equals t. And on the calculator, 5.8. So I'm just typing that carefully in. Yeah, and ln isn't a number, so it's not cancelable. It's a function. Yeah. That's it. So in this case, it would the 5.8 would mean it would take 5.8 years for our $100 to grow to the $200 at that interest rate. Yes. Yeah, but that's the only time we could cancel. Yeah. Good. Just for kicks, if you have just typed this thing into your calculator and got 5.8, change it to log and log. Use the common log button instead of the ln button. So do log of 2 over 12 log of 1.01. Can somebody do that real quick? And for those of us waiting, what are we going to get? Do it in your head. 5.8, right? Doesn't matter what base you use.
When you're talking about base, is that like I know like we use base 10 math. Is that what that's talking about?
Yeah.
So when you use P, it's like using base.
Yes, it is. It goes back to our definitions of logs here. You know, the fact that we use base 10 means that 325 really means 3 times what? 10 squared, right? Plus 2 times 10 to the first plus 5 times 10 to the 0. That's 5 ones, right? Okay, so that's what base 10 is. It's all about powers of 10. So here, ln of x is about a power of e, right? Okay, so I think that is good. Any questions about this inverse stuff or log stuff before we jump in on the activities? Okay, they start here. If you have homework, take it out. I will pass out the quizzes from Monday and raise a flag if I can help.